This is going to be really quick. It's just a 10-minute lightning talk, which now has 7 minutes left of the 10-minute slot. So, Osmo RemSim, the remote SIM card software. As Kevin has just presented, we have done some development on the SimTrace 2 firmware, where there were some commercial or user requirements to implement SIM card emulation and SIM card forwarding in these kind of features based on the SimTrace device. And the code that is in the SimTrace 2 Git repository is really you can use it to demo it as a proof of concept or something, but it's not really a production software that you could use to manage lots of SIM cards and lots of remote SIM card emulators in any way. And that's what Osmo RemSim is about, which is, of course, free software, just something that Kevin mentioned. While SimTrace is an open hardware device, the Sysmo QMod is not. It's a proprietary hardware device, but the firmware and the software is open source. And here, the Osmo RemSim software is also open source, so just to be clear on that. So SIM card forwarding, in principle, unrelated to the specific stuff that we are working on. I mean, what do you have? You have a SIM card, you have the SIM card implementing an electrical interface according to ISO 7816-2 and -3. You have a card reader of some sort. Typically, that card reader will implement a USB CCID profile. That's a standard USB profile that's implemented by almost all card readers today that attaches to some computer. And then on the other end side, you have another computer, which then has the SimTrace 2, actually in this case, attached. And then you have this flexible printed circuit that looks like a SIM card in mechanical form factor inserted into a phone. And so we are basically taking the phone queries the SIM card for something. We're taking that communication, picking it up with the SimTrace device, sending it over USB into a computer, sending it over a network, picked up by another computer, sending it over USB into a card reader, over the protocol into the SIM, and then the entire way back. That's basically the forward. Now, why would you do something like that? Well, the first answer is, of course, always because you can. The second answer is there are actual real-world use cases, and they have been around for at least 15, 20 years. You can find commercial products in that market which are used for automatic roaming testing, where you have the problem that you have, I don't know, 300 operators that have roaming agreements with 300 other operators, and in order to test them, and they need to test them regularly, each of those operators needs SIM cards of each of the other operators locally in the country in mobile devices that are attached in that respective network. So you have this full mesh of every operator having to manage at least 300 or whatever SIM cards from all the other operators, and that can become quite a mess, and then the SIM cards may get lost, or you have a new SIM card that you want to test, so you physically have to ship it there, and it becomes basically rather unmanageable. So there are companies offering systems that can do all this roaming testing fully automatized, and so every operator just has his own SIM cards in some SIM card rack somewhere, and it can dynamically provision that into any visited network that he has a roaming agreement with to do automatic testing there. The same is true for voice quality testing. There's a lot of so-called over-the-top interconnection fraud, which means that operator A is actually paying for a high-quality voice connection from A to B in terms of interconnect, but then there's some intermediate party that basically uses whatever mechanisms to route or transport that call that doesn't fulfill the quality guarantees, so you want to continuously test whether the voice quality you pay for is actually the voice quality you get for. And there's also reasons or applications where this is useful in cost optimization cases. So let's assume you have you're on a vessel and you're traveling on the ocean, and you're traveling through very many countries. If you wanted to, you're next to the coast, and you could theoretically use LTE or 3G to communicate in that country, but you always have to get a local SIM from that country to avoid ridiculous international roaming charges. But you also may have an Iridium or whatever backhaul from that vessel over satellite. So you could just have a central data center where you have SIM cards from all countries, and then you dynamically provision that SIM card over satellite into the respective vessel, so it always has a local SIM card at the coast in front of the respective country. So there are applications like this that are possible with remote SIM systems, such as the Osmo REM SIM that we now implement. Now, in a very simplified diagram, we basically have the data center with readers and SIMs on the left-hand side. We have the actual like SIM trace device or Sysmo QMod or whatever other device on the phone or modem device. And the SIM card and SIM readers are normal unmodified devices. We use CCID USB profile, we use libCCID and PCSC Lite, the standard stack on Linux. And we have a software called the REM SIM Bank Daemon, the remote SIM Bank Daemon, that serves, in this simple example, a single reader with a single slot with a single card. On the other hand side, we have the REM SIM client, which attaches to the SIMTrace2 device, which then attaches to the actual phone or modem. And there is a protocol that we came up with called RS Pro, the remote SIM protocol. I like the Pro. Used to communicate over the network, and that's basically in the middle. We use an IPA multiplex. Why? Well, because we want to have TCP and we want to have preserve message boundaries. And since we have that implemented in any programming language, whether in TTC in 3 or in Erlang or in Python or in C by now, then we just use that multiplex. And we use an ASN1-based protocol definition with BER encoded messages going back and forth between those two elements. So the full picture in a more real deployment looks something like this, and it's still a very small deployment. So we have something which we call the Sysmo Oct SIM here, but you could also just as well have 8 individual USB card readers on the left-hand side that attaches to various SIM cards. And you have the Bank Daemon still in your data center. And on the client side, you of course have multiple of these, and each of them has a REM SIM client and a SIMTrace2 device and a phone or modem. And you have RS Pro-based connections in between. One element that's new here is the REM SIM server in this diagram, and that's basically the entity that manages all the different elements. So every bank will first connect to the server and wait for further instructions. Every client will connect to the server to wait for further instructions, and the server then configures and provisions which particular slot in which physical SIM bank connected to which bank daemon is currently mapped to which particular remote client connected to what particular phone. To manage those mappings and manage the status and get notified in case of some errors or some SIM card being removed or damaged or no longer responding or what's on. Yeah, what's the status of all this? osmoremsim.git is on gitosmocom.org for about a month or more by now. The Bank Daemon exists and it can serve a number of card readers and SIMs. We're currently testing with 5 during development. It's an unlikely Osmocom program in that it is multi-threaded because the PCSC APIs are blocking. There is no non-blocking APIs to standard APIs to use smart cards. So we basically have 1 thread per slot or 1 thread per SIM card. And there's almost no state shared between the threads. So it's only the mapping that basically needs to be shared, the mapping table between the threads. Then we have the REM SIM client, which is again a normal libosmo core single-threaded asynchronous event loop-based program, which works with the firmware from the SIMTrace2 Git repository to talk over USB to the device, and then also implements again this ASN1-based protocol with IPA multiplex on the backhaul side, so to speak. And the server manages all these dynamic mappings and so on. The code, including a D, is still undergoing development. It's not ready for deployment yet, but you can already run it as a proof of concept, and it will actually do its thing, and with no dynamic mappings yet, but with static mappings. Okay, and that's it. Yeah, started 2 minutes late, ended 2 minutes late. Great. Any questions on this? Yeah, let's start with Max and then Peter. Well, Peter Stuge.
We use RS Pro protocol. Are there any What other vendors use? What kind of protocols? Any standardization efforts in there?
No. There is no standard protocol for that. There is no standard for any of what we are doing, and so in this project. So the RS Pro is just a self-invented protocol, and to make it easier to have parsers and encoders for different programming languages, it's specified in ASN1. That's basically it.
So what's the load that you've tested so far? My concern is that the PCSCD may not be may become a problem if there's a larger deployment, and it might be worthwhile to just cut all of that out and CCID directly from the BankD.
Yeah, you could, of course. I mean, that's a possibility. The PCSC is also, as far as I understand, multi-threaded or multi-process.
Yeah, yeah, good question. I think it's multi-threaded, yeah.
I think for every reader you have actually one process. So
yes.
The number of slots in PCSC daemon is limited to 16 or whatever by a compile time default. But as far as I understand, you wouldn't have more than 16 readers. No, 16 slots within one reader served by one particular process. Yes, there is then the central PCSC daemon that manages all the state. But I mean, we're talking about SIM card communication here. This is in the maximum, it's something like 300 kilobits per second per card on peak in the maximum in a very fast card. So, you know, I think it's not really something that has to be too concerned about. Also, I mean, you probably wouldn't go for PCSC and USB CCID profile for really large numbers of readers. So if you're thinking about SIM banks that have like 1,000 cards or something like that, they don't implement PCSC anyway. So they have some custom proprietary whatever protocol, and then you need something like a RemSim bank daemon that then can talk to that rather than PCSC and so on.
Yeah.
Hi. So I'm imagining myself deploying a SIM trace with a single board computer, like a Raspberry Pi, on site on multiple locations across the globe, and from my data center, having multiple SIM cards with all the operators that we have agreement with, okay, doing on-site testing remotely, okay, thanks to the remote SIM bank and remote RemSim client. And I'm wondering how much of that is a fantasy or can be really implemented using this.
There's nothing fantastic about it. I mean, it's not that this hasn't been done in the industry before. I mean, we're not the first doing this. You can go and buy this from suppliers for whatever amount of money for years, at least for, I would say, 10 or 15 years. So there's nothing magic about it. It's really just that we are doing it with open source software and at least in normal standard off-the-shelf hardware, except for the part where there is no standard hardware, which is the SIM trace side.
Okay, then cost-wise, okay, is a can the RemSim client and the libraries needed for the SIM trace be run on a Raspberry Pi, for example?
Yeah, sure. I mean, if you're talking about something like 100 kilobytes large executables that are written in C, I mean, you can run it on
whatever.
You know, probably on UC Linux if you want to.
Okay.
It's there's no performance requirement.
We'll give it a try.
One more question there, and then we head into. Oh, sorry, there was
Hello. I'm guessing if you had a link. So let's say that you had a very remote, diverse link. So you had something like it was connected over VSAT, or it wasn't necessarily the most reliable, stable connection. I'm guessing you could, with SimTrace, respond to the ATR or man in the middle, the ATR from the card, to slow the speed down on the link between the card and the UE, therefore giving you a bit more time to get your processes across a long latency link. I don't know if you even tried that. I don't even know if it's possible, but I'm guessing. I know the ATR gives you the speeds, so.
We are actually doing this, but that doesn't really determine the, how can I say, the actual application layer latency or maximum. It doesn't determine the upper bound for the maximum latency. because in the T=0 protocol that's spoken between a chip card and the reader, there's something called waiting time extension. And so basically, let's say the phone or the modem sends the run GSM algorithm command to the SIM card, then there is an initial waiting time, how long the card reader in the phone will wait for the card to respond. And if the card is not finished supplying that response in time, it can ask with using, I think, 0x60 hex or whatever.
Yeah, more time.
Yeah, it can say, oh, I need more time, I need more time. And there's actually, according to the spec, there is no upper boundary how often you can do that. There is no maximum number of waiting time extensions. Of course, in reality, the baseband stack of the phone will give up at some point. What's the determining factor is the time the authentication, no, sorry, the MSC/VLR will wait for the response to the authentication command, and that's typically around 4 seconds. And that's much longer than any VSAT link or whatever you have in the chain. So, and that's irrespective of what kind of baud rate you use. That's a separate.
Yeah, I was thinking more in terms of if you had situations where the process was unreliable and you could put it down to something, you know, electronically rather than necessarily logically.
Yeah, no, what you do in that case is you, as Kevin indicated in his previous talk, you really emulate basically most of the SIM card locally next to the phone, all the, you know, read file, write file, all the update binary, all these commands. You just do that all locally. You don't really transport it over the link, and then the only thing that's remaining is the run GSM algorithm and the response. And then I mean, that's so small, you know, you could do it over packet radio probably.
Just to comment on that, we are currently swapping the ATR and putting the smallest one while debugging, but we want to do the inverse, because if you have a not fast card reader or not fast SIM card, then you have some delay, and SimTrace is capable of doing high speed. So we will have the option to actually say we support high speed, and this way we can also, it's not a lot of minimizing, but we will minimize the traffic even more if you have everything locally. And if we need more time, then we can still extend it. So there will be the option to either have it slowly to debug it, have it fast to really be fast as you can, or really use the real ITR, because it doesn't only encode the speed, but there is also some other data there which the reader might be interested in.
I hate to cut the discussion short. One last question over here, and then we have to go into the break. Otherwise, there is no break left.
Yeah, is there a possibility to remotely reset a SIM card?
Yes, because I mean, in this scheme, like I presented it, we're talking about PCSC readers here, basically on the card side. So there's the SIM card, there's the reader, and the PCSC or CCID reader, you can always reset the card. So the only thing that's needed, and there's actually already a provision in the protocol here in the RS Pro, so the SIM card can be reset. And actually the idea is that when the modem resets the emulated SIM card here, that then this gets transported over here, triggering a real reset also remotely on the card. So the state is actually reset if the modem wants to reset the card.